Okay, someone was asking a question.
Yes. Last time لما دخلنا السيمبسونز 1/3 rule و 3
Yeah,
over 8 rule مش قلنا كمان إن الerror is proportional to h power 4
مظبوط مظبوط صح.
يعني نفس الشيء بيناتهم المسج بيطلع.
إيه يعني كاوردر yes كاوردر yes it's true. اوكي بس ما عنده نفس الفورم اوف ايرور لانه انت بتعرف الايرور هي proportional to h4 بس الكويفيشنت اوف proportionality بيفرق ساعتها بس الاوردر هو ذاته.
اوكي
Just what is your name?
جورج.
Okay, George. So now, when we used composite trapezoidal rule, the error was of order h square. By applying the first correction, we increased the order to 4. And now you can prove that each time you correct, and now this is the first correction. Now you can perform a second correction. So now you take the updated value and you do again Richardson extrapolation to get a new estimate of your integral. And now you expect that your order will also gain 2 orders of accuracy. So now your solution will be of order 6. Okay, let us see this numerically. So the idea was I started first by a certain method. I selected the trapezoidal rule, which is of order h square. I calculated I21, I42, I84. Now from these calculations, I can do, this is the first correction. Now I will do the first correction. I will gain 2 orders of accuracy. So from here to here, I have +2. So now I can get, this is I1, this is I2, this is I4, and this is I8. The subscript will stand for the number of segments used. Now I am combining I1 and I2 to find I21. So now this is the first correction I did between these two. Now the first correction between I2 and I4 will give me I42. And when I combine I4 and I8, I get I84. So all of these consist of the first correction. And now I am ready to do a second correction. Also, I expect, we can prove mathematically, but you are not responsible of the proof, that each time I do Richardson correction, I increase the order of accuracy by 2. So now this is my second correction. So I expect now my error to be proportional to h to the power 6. Okay. So now by combining I21 and I42, I obtained always how you name it. You put the more accurate estimate هو تاني واحد. And you start by the subscript of the most accurate estimate, which is I42, followed by subscript of the less accurate estimate, which is I21. So this estimation now after the second correction is I4221. And now when you use I42 and I84, you get, this is also a second correction, you get I8442. Okay. And you can continue with correcting. So now if you do a third correction, you expect also to increase your order of accuracy by 2. So now your error is for order 8. So now by combining these two, you will get the following result, which is I8442 and 4221. Now you can see that I cannot see any change here. When I combined I4221 and I8442, I got nearly same result. You know why? Because if you want to have an improvement, you should take more digits. So already at the second correction, after the second correction, already your result is accurate up to 1, 2, 3, 4, 5, 6, 7 digits. Okay, because if you continue to correct, you will still obtain same digits here. So to improve your prediction, you should use a higher number of digits to see a difference. So here you can say it's a pretty good stage because already I am dealing with 7 digits, which is good. Okay, and you will obtain a very small relative true error in this case.
دكتور بس
Yes.
هون
Yeah.
ب 16 over 15 و minus 1 over 15 من وين
Yes.
هيدول؟
Yes, we will develop them together. Okay. انتم برأيكم كيف فينا نجيب ال 15 over 16 over 15 وال 1 over 15? Who has an idea about how to get them? So how we can come up with these formulas? What do you think we should do?
دكتور لازم نضرب 4 over 3 بالاي 42 اللي قبل و minus 1 over 3 بالاي 21 اللي قبل.
No. Look, خلينا نرجع للديريفيشن الأساسية. اتفقنا؟ احنا هي من وين جبناها؟ جبناها على أساس إنه الريشيو، جبنا الريشيو of errors أول شيء. أوكي؟ رجعنا جبنا general expression تبع الانتجرال function of the ratio of errors. We replaced ratio of h by 2. Then we are doubling the number of segments. Okay, and h1 over h2 equals to 2. We will now go over the same procedure. Okay, so as we demonstrated together, the virtual error h21, okay, over the virtual error h42 is equal to 2. When we are doing, because we started by, we are considering a particular case and the ratio of h is divided by 2. برجع بعيد. إذا مش كان divided by 2, instead of doubling the segments, if you triple the segments from one step to one step, very simple. You go back to your initial formula. I go back to this state here. Okay. In this state, just بدل ما أحط 2 مطرح h1 over h2, I can replace this by 3. Okay, and I will obtain a new coefficients here, but the procedure is exactly the same. Okay. So now, since I'm still dividing by 2, يعني بعده الريشيو over 2, بس الerror بطلت الريشيو of error بطل h1 over h2 square تغير, because now we did a correction of the correction. فأنا وياكم شفنا إنه when we did a correction شو صار بالorder? The order increased by 2. يعني now instead of having the ratio of errors equal 2 to the power 2, يعني إذا بتتذكروا هونيك وقت أخذنا الerror of h1, okay, over الerror of h2, لما كان عندنا h1 double h2 بيطلع الريزلت equal to 2 square. بينما هون, since we are now dividing the error obtained with virtual step h21 over the error obtained with virtual step h42, this will be equal to approximately h21 over h42 now to the power 4. And since I am doubling segments, يعني ratio of virtual errors h21 over h42 with 2, بيطلع لي approximately 2 to the power 4. This means that I can replace the error obtained with h21 by 2 to the power 4 times the error obtained with h42. And now if I use this replacement, I will get the formula you have seen below, because just by doing this, first I get a general rule as I did in the previous case. Okay, the general rule is the following, that now if I combine the integral I get from h21 with the integral I get from h42, I will get the following, because this first estimate of the integral, so this is why I can say that I is I h21 plus the error involved when using h21, and also at the same time I is equal to h42 plus the error involved in h42. And since I did a relation, I approximated a relation between these two errors, I can replace just all I have to do is to replace my the error h21 by its expression function of h42, and I will end up with the following result, that the correction of the correction, So now I4221, okay, is equal to I that I computed using H42 plus IH21 minus IH42 over 1 minus H21 over H42 to the power 4. So it's exactly the same result I obtained in the first correction, but just now the order of the error increased by 2 instead. So instead of being 2, it's now 2 plus 2, it's 4. Now, in particular, if I am doubling the segments, and if I'm using a ratio of H of step sizes 2, then I can replace H21 over H42 by 2. And I get that I4221 is equal to IH42 plus IH21 minus IH42 over 1 minus 2 to the power 4. So just I have to replace this term and you have to find the coefficient of IH42, you do 1 minus 1 over 1 minus 2 to the power 4, while for H21 the coefficient will be 1 over 1 minus 2 to the power 4. This will result in a coefficient of 16 over 15 for IH42 and minus 1 over 15 for H21. And again, you can now update for any correction, and for the third, fourth correction, for any correction you do, you can find a new expression, okay? Just to update the order. And the second thing to do is to, depending on the ratio of H, you replace the ratio of H by its value, and you get the coefficients of correction. Okay? Is it clear? Try if you want to derive the following coefficients. So now if you follow the same procedure, when doing the third correction, just what will change is the order. So instead of dealing, now if you want to try it first so this is the first correction. It was 2. The error was proportional to the ratio of H squared. Then here, the ratio of error was proportional to the ratio of H squared. When using now the second correction, which we did together, the ratio of errors were proportional to the ratio of H to the power 4. And now you expect that when you do the third correction, the ratio of error will be proportional to the ratio of H to the power 6. So this is how you can get an estimation of these coefficients here. Try to derive these coefficients using the same procedure. Okay? Any question on this? Okay. So this is the Richardson extrapolation method, also called Romberg integration. Okay. Now we will move to another method that will improve also the accuracy of a prediction of integral. Now we will go back to enhancing the trapezoidal. Because if you remember, the advantage of the trapezoidal rule is that you are using a first order equation. So your computation will be easier. But it represented the disadvantage of high error when you have high f-seconds. So when you have high curvatures, the trapezoidal rule will not work very effectively. So what can be the solution? We said why to not take advantage of considering a linear profile, which is a very simple profile, but reducing this error. How we can do this? From here, we thought about, instead of taking this line passing by the extreme points, so the two data points here where the straight line will pass by are the extremities of your trapezoid. So why to not take them somewhere in between, not at the extremity? Because this will be very helpful. Why? Because if you look at the following figure, if I don't have these points at the end of my trapezoid, then my prediction will be much better. Why? Because here, for example, here, I am overestimating the integral. So I will have a larger value for the estimation. While in this part, I have an underestimation of the value. So here, I will have a lower value for the estimation. So here it's minus. And again, here I have an overestimation. So I can say if I can try to find optimal positions for my 2 points, I can end up with the exact value of the integral. And if I put the 2 points in a way that the positive areas cancel out with the one which is considering as negative since I have underestimation, then I will be able to have an error of 0. So by proper selection of positions of these 2 points, I can overcome the disadvantage of the trapezoidal rule. From here comes the idea developed by Gauss. So this is called the Gauss quadrature, and we will go over it. How to find these positions? This is the challenge. How to find the optimal positions of these points in a way to give an exact value of the integral. Okay? Now, just for you to understand the procedure we will follow, we will take first a very simple example how to get coefficients. Okay? So we will start by the simplest case where actually we take the points at the end. So we know the positions of points, but let's say we don't know the coefficients that should be used to multiply them. What do we mean by this? The idea of Gauss quadrature is that I will write the integral. So here, I will start by the general rules and do the derivation for first the trapezoidal rule and then for general rule. So here the idea is I should get what is the position of the 2 points that will minimize, that will give me an error of 0. So I will call this point x1 and I will call this point x2. And I will say that if I select appropriately these 2 points, I can end up with the exact value of integral. So the exact integral, okay, of the function of I have integral of x in the interval I selected, let's say between a and b, okay, should be equal to a certain coefficient c1 times fx1 plus another coefficient c2 times fx2. So here, if I don't know anything about the locations, I have 4 unknowns. The coefficient multiplying fx1, the position of x1, the coefficient multiplying point 2, and the position of point 2. So here, in this case, I have 4 unknowns, so I need 4 equations. We will see together how to get these equations. Okay? But before, to understand the procedure, we will start by a simpler analogy that we will do. So we will say, at the first stage, I will consider that the positions of the 2 points, I will take it as the extreme position of my trapezoid. So as we did in the trapezoidal rule. So I will take this is A and this is B. And you want to develop a method to come up with the coefficients C1 and C2. Okay? And this method that we will develop here will be also applicable for any location of points. So we will extend it then to find what are the 4 unknowns. So if we don't know where the points are, we have 4 unknowns if we are taking 2 points. If we fix the location and we want to find the coefficients, we have just 2 unknowns. So now we expect that if we fix the location of the 2 points at the edges of my trapezoid, this means that C0 or C1 and C2 should be equal to the coefficients I got using the trapezoidal integration. And we will demonstrate this together to develop the general method out. Okay? What will be the idea here of Gauss quadrature technique? The idea is to find undeterminate coefficient. Okay? And how to find this? We will consider that we want to predict exactly the integral. So my purpose is to exactly predict the value of integral between a and b of fx. Now, if I want to use just the ends of my trapezoid, this is not possible in all cases. To obtain the exact value, I can only have 2 scenarios. Or I have a constant line, or I have a constant line, or I have a straight line. If I have any curvature, using the extreme points, I will not be able to predict exactly الانتجرال إلا إذا الفانكشن is very particular. يعني if I have, let's say, the function بطريقة إنه كانت positive part will cancel out the negative part, but ساعتها it will not always work. Will work in a certain specific case, and I want to develop a rule that will always work. Okay, this is why I will say that if I fix my ends here, my 2 points, I expect that always I can get the true integral in 2 cases, if my function is constant or if my function is linear. Okay, and now we will see how to calculate C0 and C1 based on this. Okay, so first we will say that this method will give me exact result for first when I have a constant function. So let us go now the first equation to find the first equation relating C0 and C1. So since we predict the trapezoidal method will yield an exact solution for constant function f(x) equal 1, then I will say if I consider a constant function equals to 1 and the length of my interval is b minus a, I will take this interval centered over 0. So my 2 endpoints will be minus b minus a over 2 and b minus a over 2. Okay? And now I will say, let us predict what is the first equation relating C0 and C1. All I have to do is to apply the rule. Okay? So I will say C0 times f of x1, and here x1 is this one. So because you consider that your 2 points are the end of your trapezoid, then the first point is, so x0 is minus b minus a over 2, and x1 is plus b minus a over 2. Okay? Now, the second step will be to perform the integration by just replacing the value. Since here you are considering fx equal 1, so whatever is x, you will get 1. This is why f of minus b minus a over 2 is 1, and f of b minus a over 2 is 1. So your resulting relation will be c0 times 1 plus c1 times 1 equals to the integral of equation 1 dx between fx equal 1 between minus b minus a over 2 and b minus a over 2. When you perform the integral, because it's a constant, you can take it outside of the integration, and then just you have b minus a. Okay? So you can say now that the first equation that should relate to coefficients C0 and C1 is that C0 plus C1 is equal to b minus a. And this is not enough. We need a second equation to close the system. This is why you will say, I expect that the trapezoidal rule, when using 2 edge points, can give me the exact integral for 2 cases. The first one is constant function, which we did here. The second case is when my function is linear. Okay? So now I will repeat the same procedure, but now I will say that I expect that this trapezoidal method can give me the exact value if my function type is linear. This is why I will repeat the operation and say that C0 times f of x0, which is minus b minus a over 2, plus C1 times f of b minus a over 2, which is x1, is equal to integral of function, the linear function x, between minus b minus a over 2 and b minus a over 2. And now I proceed. What is f of minus b minus a over 2? Since I'm dealing with function of fx equals to x, then f of minus b minus a over 2 will be equal to minus b minus a over 2. And f of b minus a over 2 will be equal to b minus a over 2. Equals to, we know that the integral of x is x squared over 2. So we perform the integration between minus b minus a over 2 and b minus a over 2. And therefore, we will end up with a second equation. And this second equation will relate C0 and C1. So now I end up with 2 equations with 2 unknowns. And if I solve them, I can get my coefficients C0 and C1. And we will see that C0 and C1 will give me again the formula obtained by trapezoidal rule, which is the following, because you are estimating the integral I by C0 times f of x0, okay, plus C1 times f of x1. And now, if you just replace your values of C0, C1, and x0, x1, so first for C0, it is b minus a over 2. And also C1 is b minus a over 2. So you can take b minus a over 2 into factor. Times what? Times the summation of fx0 and fx1, which are here the endpoints of my interval. Okay? So I got, again, the trapezoidal formula, which consists of computing the integral as the mean, the average, the actual average value. So this is the estimate of the mean value of your function, fx0 plus fx1 over 2, times the width of your interval. So this is, we just repeated the derivation of trapezoidal rule to tell you about the approach used. Okay? Now, what will be more challenging is that I don't know the locations of the 2 points. So for the trapezoidal rule, I know I will take my position of 2 points at the edges of my trapezoid. While now, to get higher order accuracy, we will have to select the optimal position of the points. So from here, the idea of the 2-point Gauss-Legendre formula. Okay? So instead of taking the 2 points here at the end of my trapezoid, no, I will say I will try to find what optimal location of x0 and x1, what should be these locations, in order to obtain an integral, which is from trapezoidal rule, this integral, okay? When I perform this integral, I will find the area under this curve, okay? But now, instead of computing the integral by just considering that I will take a function and I will find the area under the curve, no. I will take points that are in between, not at edges of my trapezoid. And I want to try to have exact value of my integral for functions that have higher order than a linear order. Because already the trapezoidal rule, when I take the points at the end, will be able to give me the exact value for constant function and for linear function. But it will not be able to give me the true value for a quadratic function or a cubic function. I will have an error. If I don't want to have an error, I should select points at a certain position that is different from ends. And the objective here is to develop a method to know what these positions are. We will see now together that if you have only 2 points, you can reach, with this method, you can be able to predict up, you can have the true value of the integral for an order of x3, yani for a cubic function. So in this way, a first order function will help you into getting an exact integral for a third order function. This means that Gauss-Legendre formula will allow you to increase the order of computation by 2, which is very good. The whole idea is, the only challenge here is to find what are the positions. So what will be the method of thinking here? Now, when I fixed the points at the ends, I only had 2 unknowns, C0 and C1. Now, since I want to vary the positions of these 2 points, I will end up with 4 unknowns. And 4 unknowns will require 4 equations. Can you tell me, from what we did before, from the method we developed before, what do you think will be these 4 equations?
بدنا ناخد constant function بعدين
Okay.
f of x equals x
Very
بعدين
good.
x squared بعدين x cubed.
Excellent. Bravo. It's George, ما هيك?
Yep.
Okay. So here, The whole idea is now when you don't fix the points, you want to find them. This will allow you to increase your order of accuracy. Why? Because you will select them in a way to give you an exact integral for a constant function. So here order 0. For a linear function, which is of order 1. For a quadratic function, which is of order 2. And for a cubic function, which is of order 3. Okay? So now, how you can obtain this? By just finding 4 unknowns in a way. So since you have 4 unknowns, you are allowed to write 4 equations. So you will force your C0, x0, C1, and x1 to satisfy 4 conditions. The first one is that it will give you an exact estimation when the function is constant. So the first step, you will say that with these coefficients, I want to obtain an exact computation of the integral when my function is constant. So the first relation will be C0 of x0 plus C1 of x1 equals to integral from, first, in the first approach, we will take an interval of -1 and 1. And we will see after together how to go over this. And if I give you any interval, you can transform it to this form. We'll see how. But just now, I want you to understand the idea. So starting from an interval from -1 to 1, I will integrate first the constant function. Okay, and I expect to get exactly the same result. So here, since I started with a constant function, f of x is 1 everywhere. So f of x0 will be 1, and f of x1 will be 1. So the first equation will be C0 plus C1 equals integral from -1 to 1 of 1 dx, which is 2. So this is equation number 1. Now, as George said, I will force my equation to give me an exact value now for a linear function. Okay, why I can do this? Because I have 4 unknowns, so I can find them in a way to satisfy 4 conditions. The first one is to give me an exact integral for a constant function. The second one is to give me an exact value for a linear function. The third condition is to give me an exact value for a quadratic function x squared. And the fourth one will be to give me an exact value for a cubic equation. So by forcing these 4 equations to be, I can get the 4 unknowns, which are C0, C1, x0, and x1. So I will know what are the positions, the optimal positions I can select to being able to calculate the exact value of the integral up to an order of 3. Okay, so now the second equation will be obtained by just saying that I want to force the integral obtained by doing C0 of x0 plus C1 of x1 to be equal to the exact integral between -1 and 1 of the linear function x dx. So all I have to do now is to say what is f of x0, since I'm dealing with function f of x equals to x. So f of x0 is x0, and f of x1 is x1. And now I will perform the integration between -1 and 1 of x dx, which will be 0. This will allow me to get my second equation. But of course here, 2 equations are not enough because you have 4 unknowns. Your unknowns are C0, C1, x0, x1. So now I should move to the third equation. And as we said, the third relation will be obtained by forcing the integral obtained by C0 of x0 plus C1 of x1 to be equal now to the integral from -1 to 1 of the function x squared dx. So now, since I'm using function of x equal x squared, so I will replace f of 0 by x0 squared, and I will replace f x1 by x1 squared, and then I will integrate between -1 and 1 the function x squared dx, which will give me 2 over 3. So now I was able to get my third relation, my equation number 3. And to end up, to close my system of 4 equations with 4 unknowns, so I need to do the last step, which is to force the general form of my integral to be equal to the exact value of the integral of a cubic function x cubed. So I will do C0 of x0 plus C1 of x1 equals to integral between -1 to 1 of x cubed dx. And now, since I'm considering a cubic function, then fx0 will be replaced by x0 cubed, and fx1 will be replaced by x1 cubed. And integral between -1 and 1 of x cubed dx is 0. So this is my equation number 4. And now, all I have to do is to solve 4 equations with 4 answers. Okay? If you solve the system, you are not responsible of how to solve the system. It's a nonlinear system. I just want you to know that this is the solution. Okay? So you get C0 plus C1 equal to 2, C0x plus C1 x1 equals to 0. Here you have 2 over 3, and here you have 0. So you can deduce that if I select the 2 points, so the position of the 2 points between -1 and 1 will be as follows. Here it is, the first x0 is -1 over radical 3, and x1 is 1 over radical 3. So what is very nice about this result is that this integral is third order accurate, but it is just using a first order function. I'm using a linear function, but I am selecting the 2 points in a way, in an optimal way, to give me exact value for even a cubic integration, which is a very powerful technique. This is why the 2-point Gauss-Legendre formula is very important. Okay. Next time we will continue this chapter. Any question on what we did today?
دكتور
Yes.
هون شو هي الاف تبعنا يعني؟
الاف هي الفانكشن تبعك شو ما تكون.
اوكي.
يعني
مش
انا بعطيك
approximation
يعني انا فيني اعطيك حيلا فانكشن، فيني اعطيك فانكشن اذا بعطيك اياها او كونستنت او لينير او سكند ديجري او ثيرد ديجري، بتكون اكيد انه الانتجرال اللي بتطلع لك هي اكزاكت. اذا بعطيك مثلا x4 وx5 بيطلع لك الابروكسيميشن منيحه، لانه هي الميثود تبعك ثيرد اوردر. يعني اذا بتستعملها مع x4 وx5 we expect انه you will have an error of order 4 وطلوع. اوكي. يعني ال error will be proportional to to the first derivative مش to the third derivative ولا to the second. يعني نحن عادة trapezoidal كانت proportional to the second، صح؟ لأنه هي first كان عندنا نحن عم نستعمل linear function اللي هي first order، we expect إنه a first order function will not be able to حتعطينا error proportional to f second، صح؟ هيدي كانت بالترابيزويدال. بس وقتها نحن نقينا البوينتس in a good way بطريقة إنه it will give us exact value even for third order function. بهيدي الطريقة علينا ال order of computation من error of order 2 okay ل error of order 4. This is why we say إنه now كانت الترابيزويدال method first order accurate لأنه كانت الerror تبعها order 2. هلا صارت by using the 2-point Gauss-Legendre formula we were able to reduce the error now to order 4, then the integral is third order accurate. Okay?
Okay, thank you, doctor.
Welcome. Yeah, let's see you next time. Let me check if you have questions in the chat. Yes, of course. Today I will post the homework. Sorry for being late, but no, I am preparing a big homework on all chapters. Today I will post it. Okay? Bye.
دكتور هيدا last chapter.
No, بعد في هيدا رح يخلص، بعد في just one last chapter. We'll go over it next week. Okay?
Okay. Bye, doctor.
Bye.